able to attend. There we go. Okay. So again, as usual, welcome everyone. So we hope that you had a nice undas break. No, some of us probably even nakapunta sa probinsya and spend. Hopefully, you were able to spend some time with your family. Pero yeah, we're back again. Thank you for being with us here on a Saturday. Now, even though it might be a rest day for most of us, but yeah, thank you very much for being here to learn and to explore some things, especially in quantum computing. So yeah, some session norms before we start. So please engage actively, be open, and ask away. There are no dumb questions, especially for this very new topic for everyone. Yeah, don't please do not be afraid to ask when you need to. So our members are online and they will be able to reply to your messages on Discord. Okay, as I've mentioned, you can use the live questions channel on Discord just so that if there's still some unanswered questions, we can answer them asynchronously. And if you ever want to go back to some answers after the lectures, also, the second homework is still open. And yeah, it's open until November 8th. So yeah, we understand that it might be a bit challenging, especially it's very deep in notations, ganyan. So yeah, we definitely took notes of your comments. And yeah, for the next homeworks that we'll present to you, it would be much more progressive such that you would be able to do it. You won't be overwhelmed by it. Also, for the past homework, the second homework, there are some corrections. So, thank you very much for those people sa Discord that reach out to us and mentioned that there are some errors. So, thank you very much. So, there's a new document on your uh, Google Classroom tab. There's a document titled Homework to Erratum, where all of the corrections are listed. So as hopefully there na wala nang mga kailangan pong palitan corrections. Pero yeah, if we do have some corrections, please refer to that na lang. And also, we will be returning your responses tonight so that you can review, no, especially if you haven't got a high score yet, no, so that you can review and try for another or higher score. Also, we ask everyone, no, we encourage everyone to collaborate and yeah, send your questions on the homework dash help channel on Discord. No, yeah, we will try to reply as fast as we can, and yeah, you can also use the study rooms if you need to. Also, there are some questions on our hackathon. So yeah, it would be an in-person event at CITU. It would be on November 20, 2023 on Monday. The registration will start at 10 in the morning hanggang hapon yan. And also the IRR's guidelines will be sent next week to the instructors. So, dear instructors, we will reach out to you po on the coming weeks on how you can form your groups po for each representative school. Also, if you do need official invitation letters, so that you can ask for an excuse letter, no, para it's a Monday, no, it's a weekday, it's a work day. Pero yeah, if you do need an official invitation letter, we will be happy to provide those for you po, just so that you won't think about anything else and you can enjoy the hackathon fully on that event. So yeah, if you still have some questions, message us. Pero don't worry, dear instructors, we will reach out to you next week po. All right. Okay. So, very excited na ba ang lahat? So, for the past 3 weeks, we've been teasing a lot about quantum ganyan, quantum mechanics, quantum programming, yeah, and quantum computers, qubits, and all that. But we stopped on math. We've gone back on programming. But at this time, we'll be discussing finally the quantum mechanics concepts, quantum gates, Qubit States, and the Bloch Sphere. All right. So, for the first session for tonight, for this afternoon, rather, is Sir Burns. Ayan. So, Sir Burns has a lot of hats that he wears. Pero here at One Quantum Philippines, is a very active educator and researcher, no, and he is the vice president of the organization. So without further ado, very excited si Sir Burns. Kanina pa siya, very excited. Kanina siguro you heard about his vision of a quantum computer here. But yeah, he's gonna talk a lot more about it on his talk. So without further ado, the floor is yours, po, Sir Burns. Sir, you're muted po.
Okay, so how do uh, you know, okay, yes. Do you see it, everyone?
Yes po, it's clear.
Okay, so it's I guess it's early evening now. So good evening. I'm making this presentation. I'm located at the in Manolo Fortich in Agusan Canyon, Manolo Fortich here in northern Mindanao in Bukidnon. No, where it's actually rather rainy. So professionally, I work as a manager for a plantation. It's Del Monte, where I handle geomatics department. Where we're flying drones and we're mapping the whole plantation, about 28,000 hectares of it. And we're into remote sensing, drone, and also hyperspectral imaging. The entire experience was because I was former science specialist at the National Mapping Project between 2014 and 2017. Bobby and I, we met in Cebu. No? It comes a long way, no, since. And he encouraged me to join a small group before. And now we're really our organization. So um, I'm also a member of the Sambang Pisika ng Pilipinas, which is based in UP Diliman. And recently, we presented the paper sa Sambang Pisika ng Visayas and Mindanao SPBM in MSU, which we were able to write a paper on quantum variation eigensolver. It's an optimization algorithm which I tried to use in an agricultural case. I co-authored with Bobby and also with Dylan. I was also doing some years as a faculty of physics at the University of San Carlos in Cebu. And after that, I was tenured at URA at the National Institute of Physics, where I worked especially on experimental optics, signal processing, laser imaging, and um, instrumentation physics. And the last was senior science specialist for LiDAR. So um, I will not explain this anymore. I think Bobby will have already explained this one. And the lecture component overview are the following. No? For the most part, it's really very conceptual and very top level kind of discussion. We begin from simple to complex with in terms of understanding quantum. No, we don't begin from complex to simple. We begin from simple to complex. So, for example, what's the difference between classical and quantum computers? What are quantum states? Why are they discrete and probabilistic, etc.? And very important results from quantum mechanics. Now, if you want pure substance of quantum mechanics, you talk to Bobby. No, he's a theoretical physicist. I'm more like an applied experimental physicist. No, if you want me to set up instrumentation on an optical workbench, I can do that. So, and then we move to basic quantum gates and the Bloch Sphere. Again, very conceptual because our friend here, Elmer, will be dealing at more detail on the Bloch Sphere, a little more in depth. No? So, at any time you can pause me and for any questions. There are some tools that I'm going to show that perhaps that interest you. So, for example, the quantum virtual lab, it's called quantum flight trap. It's a way to simulate quantum phenomenon. It's almost like playing a game, no? But this is where you realize, for example, if you don't have an interferometer, it's very expensive to have one. but you can have a virtual RAD to build your own spectrometer. I mean, interferometer. I also would like to take you to on how to do a basic setup for having a IBM quantum lab account. As early as now, we should be able to be very familiar using it. There are a lot of many quantum computers available, but my first bite was really using IBM, so I'm going to use that. Well, we'll do a little bit of coding, but it's not extensive. I expect also Bobby to help that, and also Jabez and all the guys who are more adept to it. Okay, so now I just want to, for those people who have not seen this map, I'm always showing this to the talks that I'm giving because I want everyone in the country to be sort of aware that we are in the quantum effort world map, no? But it's very difficult to find it. It's actually here on the right side. Philippines is like $17.2 million ang ating supposed to be initial money for it, no? Parang yan ang, but compared with other countries, like France, 2 billion, 2.2, the Netherlands, 904, we're trailing behind. But the thing is that we are here. We believe that we can make it happen in the Philippines. That's why you are also here. Diba? So you can see that this amount of money would translate to a lot of businesses, a lot of jobs in the future in quantum. So like what Bobby and I were discussing, are we going to produce programmers or are we going to produce physicists? So of course, what we wanted is to produce more professionals doing algorithms and writing programs. No? Okay. Um, if you're kind of confused about everything that goes on quantum computing, well, you can download this. You can just type the map of quantum computing. It tells you the graphic of all possibilities, no? The physical realizations, what are the technology involved, the models of quantum computing, and then what are quantum algorithms and what's difference between classical and quantum, etc. This gives you a very graphic picture of things on what's happening in quantum. Example, uh, in the real case, there are really companies building this, and there are many kind of type of qubit that is used. No, for example, superconducting, trap ions, photonics, neutral atom, silicon spin quantum dots. So the mostly are really running on superconducting and photonics. No, and you can see the companies here, and these are the pros and cons of these technologies. No. In the Philippines, we have a National Institute of Physics, where I came from, and we have a photonics lab. It's a laser lab. We also have the condensed matter physics lab and a material science lab. So I think the labs can be a good source of talent and also a possible place to train if we have really a quantum computer there. I went to MSU myself, like deliver a paper there, and then we also meet some students there, and there is also a possibility there, as well as in De La Salle, in Laguna, and probably also in Batangas State University or in Bulacan State University. We're trying to get in contact to get a decent university grade quantum computer. I'm happy to happen. So these are the companies actively doing it. No, there is an IBM Manila quantum computer, but it's not in Manila. It's just a name. It's still in the US. But you can access that as a back end. So there's so many a lot. So what you see on the left is a real quantum computer. It's a conducting type computer. I have the impression that these are not bronze, but they really actually are gold somewhat. Because the conducting properties are important also, even though it's superconducting, it's probably bronze. But so you can see that the actually 3/4 of it is really a very big. It's called the diluted refrigerator because it has to operate at how many millikelvin, no, of temperature, and you can see it's like a chandelier. And this is another version, but they are being sold by a company in Finland called IBM, and this IQM Spark, And this is really for quantum research and education. We hope we get this one. But I was told by the former Region 10 DOST director that they don't finance getting equipment. What they finance is a research problem. So that means we really have to crack our heads and those attending here to think about list down everything that we can think about as a problem for a quantum computer, and then we can start talking to the UST. Okay. So to give you a little bit of inspiration, Jackie used to be in the same lab that I was in the National Institute of Physics. She did her BS and Masters and PhD here in NIP. Then she went for a postdoc in Scotland and also in UK, and then she's now heading a lab in University of Queen University somewhere in Australia, and she's a quantum physicist, and she's Filipina, no, and she studied locally the Philippines, and she did her masters abroad lang, but she's doing great, no, as in quantum, with the area of quantum. So we have actually Filipinos out there that are really in the field, no, and she's very very kind-hearted and everything, and she supports us, no. So in fact, maybe someday that if you will take your PhD, you can probably take a writer and probably take a look if you can join her lab. She's not a programming type, but she's more of like quantum optics, and she's figuring out things like quantum internet, things like that. I hope that many of us can also pursue this. Now, you begin the formal lesson. No? These are some of the fellows who really started it, like Niels Bohr, Max Planck, and Albert Einstein. You know this, no? Each of them is a Nobel Prize winner that has something to do with quantum. Now, we know that Albert Einstein is photoelectric effect. Niels Bohr is on quantum mechanics also, and also with Max Planck. No? You can use your what do you call that, chat GPT, and you just type there and it tells everything what you want to know about these guys. No? But these were foundational people who believe that there is more in physics, while the other classical physicists in the past says that all the physics were defined already, and there is no more physics to be understood. These guys they developed the area of quantum physics. So, for example, the Niels Bohr, a Danish quantum physicist, he said that if you think about quantum theory without getting DC, you don't get it. So, the more you really try to understand it, the more confused you are. That's really true, because even Richard Feynman, the famous American Nobel Prize winner in quantum field theory, I think, no, he says that if you think you understand quantum mechanics, you don't understand quantum mechanics. So that means that starting it gives starting studying quantum mechanics means you have to be ready for more and more questions. And up to now, it's in fact I think it was the quantum computer was inspired by him, because he at some point he was saying that if we want to understand quantum mechanical phenomenon, and we want to simulate or model it and simulate on a computer, we cannot use a classical computer for it. He says that we have to use a quantum computer for it. No, he said no. That's sabi niya. So in a way, parang he prophesied that really if anything quantum mechanical, it has to be a quantum computer that will have to deal with it, not a classical computer. So now, I just took this from a favorite reference I have when I was still teaching physics and undergrad physics. It's called hyperphysics. That you can see that if you branch out quantum physics, you'll see all of this. No, if you're taking a degree in physics, you cover all of this. If you're taking engineering, some of it, at least 1/3 of it. No, kasi may modern physics yung mga electrical engineering or electronics engineering, things like that. Pero not all of this was useful for the quantum mechanics part, actually, because these are really classical. But you see that if you take a look at this one, the failures of classical physics led to Planck hypothesis, dual wave, particle duality, uncertainty principle, quantum statistics. Also, wave functions, sorting equation particles are really part of like tunneling, stuff like that, really part of quantum mechanics. So we take some of the lessons in quantum physics to understand what the inner workings of quantum computers are and the basic principle of quantum mechanics. Um, I don't intend to have a very formal discussion on quantum mechanics. What I would like to orient the audience is what are the biggest lessons or key takeaways in quantum mechanics so that we can move to quantum computing, the ideas there, and we move it because essentially the quantum computer operates on quantum physics and quantum mechanics. That's why we have to understand some bit of quantum mechanics and some quantum physics. It's just that the advantage of people like Babius doing theoretical, because they can really, they can really understand the whole theory about it. But not everyone can really move to just simply making quantum computers and programming it. No, Bobby is exceptional. No, a systems programmer at the same time is also doing quantum. So some important quantum mechanics ideas. No, for example, discreteness. It quantum mechanics takes values the discrete. No, it's not like continuous, like continuous propagation of electromagnetic wave. No, it's discrete. It's like packets. No, in fact, the photons are packets. Photons is like a bunch of light energies that are pulsed, no, or sent out by impulses. No, it's a discreteness. No? Ideas like superposition. No, what is that? No, I did not show it here, but if you heard about Schrodinger's cat, no, that famous uh, paradox that they place a cat in a box that has water and a poison there, no? And then if the water is poisoned and the cat drinks it, of course the cat will die. If the cat didn't drink any water anyway, of course the cat is alive. But in because you are not yet certain what's really if the cat is alive or not, in that box it's not transparent. You cannot see what inside, and you're not looking at it. Well, quantum mechanics says the cat is what dead and alive at the same time. So it's very difficult to initially to accept that. I mean, really, the cat is what dead and alive. No, that's like two states happening at the same time. That's superposition. So, hindi katulad ng classical computer that you have true or false by Boolean logic of true or false and then one or zero. You just have either a one state or zero state, or either a true or false. The flip-flop only gives you one or zero at the other, and Q bar, things like that. But in quantum mechanics, the state of having zero and state of one can happen at the same time. So, talo, kung padamihan ng information, talo talaga ang classical computer because superposition alone, it can be any values between the state 0 to 1, And it's really always like there. Kaya qubit, hindi lang bit, qubit, no? So now you have like a zero state and one state, no? Okay, inference. So for example, interference. Now, for example, if you I don't know ako sa probinsya ano kung sa inyo like may pan doon tapos binabato mo yung pan tapos kita mo magka-create ng ripple tapos batuhin mo ulit create ng ripple and then probably two of you throw stone there create a ripple nagre-reinforce yung mga waves and they created another set of ripple things like that so nagkakaroon ng interference no and it's best demonstrated later I will show you in a double slit experiment. Entanglement, no? That's the idea entanglement. So somehow, when one is measured, you get to know what's going to be the result of the other one, even if you don't see it, or even if at great distances. Maybe it's in Mars or in Saturn, and you know the state of this, and you know that's going to be what's going to state there, no? Ano yan? Zero ako dito eh. Siguro dapat sa kanya one. One ako dito, zero siya doon eh. No? So si Doc Jackie wrote a very very easy article in Philippine Inquirer explaining disentanglement. Hinahanap ko, hindi ko na makita eh. And then, what's also very puzzling and also very difficult to accept is that even if everything is quantum and you will actually try to find out and to measure the state of that particular phenomenon, every quantum system collapses to a classical result. Ganon eh, ganon. So, katulad ng cat na nasa loob ng box, once you open the box, you destroyed superposition. You actually destroy superposition by looking at it, observing it, and making the measurement, meaning nakita mo siya. Wala na, mamamatay lahat yung superposition at babalik sa what you call classical result. Ngayon, ang diferensya rin ng classical computer with the quantum computer is that probabilities kasi ang ibibigay sa'yo ng quantum computer. Yeah, probably like this bit. Pagdating sa program, makita niyo yan eh. Okay, so, okay. There's so many of these pictures in the internet. I just took this because para mas madaling intindihan eh. So, there's this young guy, this guy called Young, that experimented, no? Like meron siyang parang cardboard dyan, tapos may nutasan niya ng maliit, slit. Tapos he let the sunlight impinge that part. And what he discovered that narrow slit, it forms a light like this. Ngayon, on the second stage, ginawa siyang dalawa, maliit pa yung dalawa. And what he observed is that there is like a formation that's center that somehow reinforces this part and this part, no? Meron na bubuo dyan. Tapos, tinignan naman yung case na, okay, I'll just open the right one and then I took the left one and then I open both. And you can see, nakakita siya ng patterns dyan, no? It's called fringes. Patterns na ganyan na sometimes at the center of this one is more thicker than and the other is it's actually slowly decreasing because this part of the light is actually interfering with this light, and somehow these are reinforcing this one is subtracting on this one slowly. No? So this experiment is very important to understanding also quantum phenomenon. Kasi ano yan eh, meron yan, yan yung demonstration ng ng interference. Okay? So pag tinignan natin to, ito is actual result using a red laser. The red lasers are about probably 630 nanometers, 620 nanometers. So maybe gas laser, something like that. Makita mo sa gitna, mataas talaga yung intensity. In fact, I'm going to demonstrate to you that we can see the pages here. So, I'm just going to use this one to demonstrate to you that I'm going to put a line here and see what's going to be the profile. So I hope this works. I've been trying to. Okay, so okay, I just got the picture of that, and then I'm going to put a line profile, this one to this. What do you think it would be? So pag nilagay ko dyan analyze, and then I say plot profile, you can see here, gano'n ang forma niya. So yung gitna, nag-saturate lang yan, but you can see the intensity is higher here, and the intensity are lowering here, dito. So this is a result of double slit experiment. Makita mo talaga that some portions are reinforcing, some others are subtracting. So this is an experimental proof already of really the double slit experiment is demonstrable.
Burns?
Yes.
If you're showing something, we did not see it. I don't know.
Really? Yeah. Okay. I'm sorry. Paano kaya ito? Okay. So, okay, open. Hindi pala pwede yun. Okay, so, I guess I have to Stop it and then share again, ano? How about that? Okay.
We don't see anything.
Ah, wala ba? Oh, I wonder why. So, teka. Too bad. Ayan. Maybe this will do. So, line. Now, do you see it now? Diba?
Yes, Burns, thank you.
Yeah. So if I took the line profile of that, you can see that at the middle, you have really reinforcing of a light there, no? Tapos the others are slowly decreasing, hindi nagre-reinforce. I'm just showing that really there is really an interference happening here, no? Okay, so let's move back to the slides here. Okay. Where is that? Okay, so tapos tayo dyan. Yung interference naman, physical evidence is really, for example, there are two guys here or fishing, no, and they have poles. Siyempre, if something is shaking there and something shaking here, it creates their own ripples, no, and they're very near each other. So what happens is that some of the waves will actually cancel it out from here. The same here, some of the waves will cancel out, reinforce. The reinforcing and also the cancellation is the same pattern that I've shown you. Okay. I was just reading something from nature, no, yung nature a quick communications libre to eh. So these Chinese researchers have demonstrated in principle quantum internet. Quantum internet. So they did it, no? So they demonstrate that, and so they are really in forefront with telecom pagdating sa kanila. So but what I'm saying is that quantum internet is already demonstrated at laboratory. So this is the setup, and it uses a Mach-Zehnder interferometer. Later on, I'm going to show you how to do a Mach-Zehnder interferometer in a quantum flight trap. So it's a photonic setup, diagram lang naman yan. But the thing is that they already were the first people who experimented quantum internet. So sabihin mo, paano nag-ooperate yung quantum internet? So of course, quantum states, hindi siya binary, hindi siya... So the network itself is also quantum, hindi siya yung LAN na ordinary, but it's also a quantum network. Okay. Now, what I show you is a something we use in a university or for demonstration, or even now it's being used in STEM high school. This is called a college physics Michelson interferometer. So the interferometer at the end, you'll see fringes like this, no? If you put a line there sa gitna, you will also see the same pattern that I've shown you kanina. It's going to be big at the center, slowly decay on the right and the left kasi makita yung spot na yan. This is the optical diagram, but you can see that meron kang movable mirror dyan, meron kang plate dyan na compensation that's silly to adjust the scattering. And then a beam splitter is nothing more than an optical device that divides light. One is going to the going up and one's going down here. Pagkatapos, since mirror yan, babounce yan. Uh, babounce yan. Tapos yung layer na to, magre-reinforce din dito, babalik, makita mo sa screen. So, ang physical setup, ito yan. No? These are like the beam splitter here. And this is like your screen here. And these are the movable mirror. Ito yung laser mo, okay? And this is the adjustable mirror also. Ngayon, paano mo gagawin niya sa quantum flight trap? So, ito yung kanyang implementation, no? So, you can simply download it, no, quantum flight trap, and you can actually use it to demonstrate. This is very nice for high school, no? Kasi it's very difficult to convince them of all the equations and everything. So, for example, nandito yan, no? You can have a Mach Sinder interferometer, for example, yan. So this is the basic optics that they use. Those Chinese guys use, no, but they were using dual Mach Sinder, and this is a components you can push it here, and in a pinaka-delete, you can come back in and you can put it back here. Mga mirrors ganun din. And you can adjust the beam, no? If you put this continuous, if you put here, that becomes a photon. And if you play that, it's gonna release the photon, and you can also increase the speed if you want. And you can see that this is a beam splitter. Part of it will go to the optical modulator. The other part goes to the mirror and bounce back. And again, they all combine here on another beam splitter. Now, if you actually change this to like some percentage, like maybe 50%, like this, like this, like that, and then you play it, you can see that the other detector is receiving it, not anymore the other one. So the phase modulator changes the phase now to a half wavelength. Now this one begins receiving it. So that means that by just changing the optics, no, you can actually direct the beam to some other detector, like that. Again, this is okay. So wait, okay, so we now take a look at quantum state and to quantum circuits. So medyo aalis tayo doon sa basic ng quantum physics at saka a little discussion on the quantum mechanics part. Kasi at the end, what we want, if we want to be technologists or programmers or users of quantum computers, is to be able to translate that knowledge in the quantum mechanics sense to something that we can move to a quantum computer. So that's why if you remain to be theoretical and you don't really want to move to quantum computing, that's going to be difficult. So it should be that the quantum physics and the quantum mechanics thing is something that you need to understand the phenomenon that you will need to operate the gates or the quantum computers. No? The better you have better understanding of that, the better that you'll be able to make quantum algorithms. Okay, kasi that takes a lot of math also. No? So in outline ko lang dyan, but here we go. No, so ito yung basic difference ng classical bits at saka quantum bits. Mahaba, but I can also send you this slide if provided you send me your email, no? A possible university email. Okay, so 1 or 0 switch, tapos sa quantum may superposition. It can represent 0 or 1 or any combination of these states. Therefore, it's more richer and more complex information. Classical bits independent of each other. Sa quantum bits hindi, because quantum bits can be entangled. Remember, the result of one will be depending on the what you have in your hand, no? For example, no? Also, classical bits are always definite state, 0 or 1. Pero sa quantum bits, they collapse, they change, and in fact, they can change with noise, no? And then the output's probabilities, no? So the measurement process is inherently probabilistic. So baka lang sa Tagalog pa, baka ito ang value, baka. Pinakamalapit kong maisip. Sabihin, sa social, most probable, sa Tagalog sabihin mo, baka ito. Di ba? So classical bits can be easily copied or cloned. Pero sa quantum mechanics, may batas dyan na non-cloning theorem. Bobby knows that, no? In quantum mechanics states that arbitrary quantum state cannot be perfectly copied. So yung bit mo na solid na 1, solid na 0, sa quantum bits, hindi yan solid na 1, hindi 0, kundi proportion yan on a little bit of 0 and a little bit of 1. It's called superposition. Sa Bloch Sphere, papakita natin yan. Tapos yung classical computer, you use error correction techniques. Oh, madami niya, no? If you're a ECE guy or a e-communication engineer, you know that. But sa quantum qubits, what's important to us is, can it potentially solve certain problems faster? No? Well, ang claim right now in quantum computing is that exponentially faster. Yan ang ano, no? So yung suitability ng pinoproblema ng quantum computing is in the area of factorization, optimization, simulating quantum systems. So factorization, paano pagganap ng prime numbers. Optimization, the least cost and the higher gain is optimization. The least cost and the higher gain, the highest gain is optimization. And simulating quantum systems, no? We're still in the era of what you call NISQ, or NISQ computers, that is noisy, intermediate scale quantum computers. Kasi wala pang perfect na hindi noiseless na quantum. Kasi nga, you know, if you raise the temperature of a quantum computer, all the electrons will suddenly move so abruptly. That's why you really have to make them stay, you know. And that means that you have to bring the temperature very, very low, like even below how many degrees of 0, no? From 0. Okay. Okay. If we want to quantify how fast a quantum computer or quantum algorithm will execute, merong merong trade-off, merong trade-off because merit, a figure of merit. No, we call it like big O notation. So pag ordinaryong factorial at n factorial, kung halimbawang 1 trillion yan, tagal doon, di ba? Tapos, ito 2 to din, matagal din yan. So, mula kay quadratic lang, mataas din yan. Linear as is, no? Pero let's say if you're able to take the square root and before you actually factor it, kung may square root, ibig sabihin, dalawa kagad na number yun na pag multiply mo, the result will be n. Or if you take the logarithm, it's going to be even less, di ba? So, yun yung mga tinitingnan natin, mga possible na mga problema na pwedeng magkaroon talaga ng sabihin mo substantial effect on the computational part. So maybe someday most of us are going to, those who are lucky may land the jobs na quantum, that they become quantum algorithm engineers. No? They try to figure out to put algorithms, and then the algorithms become circuits, and then circuits can be programmed on real quantum computers. So ang bottom line yan is that it should be that the result of the quantum should be less than the classical para may saysay, no? Merong saysay ang pagiging quantum, kasi kung malaki sa classical, malaki pa yung quantum, wala nang saysay, because we're really after na we should be able to do this faster, no? Than the classical. So yung criterion na yan, O number of whatever quantum that is, and then classical, whatever method that is, it should be less. Okay, now we're slowly moving to some part that has something to do with software. So kung sa classical computing, yung mga system engineers, software engineers, Bobby is a systems programmer, no, high level type systems guy, no? He can architect entire computer system, no, and then even write the whole thing how to make that operate, no. So, and he probably have organized things like on layers of things, no, in a network. In computing, make as a classical may tinatawag na classical stack, tapos sa quantum meron din tinatawag na quantum stack. So, anong stack? It's actually more or less a hierarchy of things in classical and quantum. Now, for example, at the lowest possible identification of things is that the lowest is the classical bit for classical computing. That's like 0 and 1. In the lowest possible case of quantum computing, it's qubits. It's a superposition, di ba? Like a state of 0 and a state of 1. And as you go up to the stack, the classical bits is produced by classical gates. And while the qubits are produced by quantum gates. So, now, if you're still doing classical, then dito ka sa kaliwa, no? If you're moving to quantum, that means that you have to believe the main ideas of quantum mechanics and the principle of quantum mechanics for your use in quantum computing. So, the gates become circuits, no? It's classical, naging classical circuit. Itong quantum gates, naging quantum circuits. Okay? I'm going to touch on this at the later part of this talk, no? We will forget completely the classical part. We will only look at the quantum part. Okay, so from the classical circuits, makakabuo ka ng algorithms and protocols. If it's classical algorithm protocols. If it's quantum algorithms protocols. So mangyayari, it's going to be like a big block diagram of things, no? Recently, the group went for a seminar with Classic, and we were asked to attend like 2 sessions so that they can give a certificate. We had to solve the problem given to us, and we have to use the software, no? Ang nasagot ko lang 2 out of 3. Pinasa pa rin nila ako sa 2 out of 3. Yung pangatlo, hindi mo lang tinuro eh. So, I was being coached by Bobby and other guys to paano ba to solve magano-gano, no? So, ganyan. So, the point is that the going up is from qubits to applications. Ang question is, nasaan na ba tayo ngayon? Some of us already began and were able to understand qubits. We're even able to do the quantum gates. And we're even able to generate the circuits using Qiskit. Qiskit is a programming language designed by IBM. There are others. May Cirq and so many others. Ang dami. Pero ang alam ko lang ngayon is Qiskit. And then Classic. No? And then quantum algorithms and protocols. And finally, applications. So madami pa tayong gagawain. Ngayon, you ask yourselves now, kung nasaan ka dito, where would you be? Or where are you starting from? Baka naman nandito ka na sa algorithms eh. Oh wow, taas mo na sa stack. You're really there on the top of the stack, no? So, and you'll see only input and outputs and block diagrams, no? No more like in the internal circuits, no more like that. Believe it or not, the classical stack is still earning very much in the world, no? It's like $1,053 billion. And it is rising at 2.27% annually. So wala pa rin tatalo sa commercial value nito. Kasi ang quantum stack, yung development na yan, is only 13.67 billion to $143.44 billion. And it's expected on 2032 na 143.44 billion lang. Dito 1,000 na nga. So medyo mabagal kung pag-usapan natin yung kita rito, no? Wala masyadong investment pero mahal talaga yung starting investment, but yung let's say reaping from the benefits wala pa masyado. Okay. Okay, now we start looking at this one. It's called the Bloch Sphere. Okay? Pwede mo kasing i-represent ang state na dalawang paraan. Okay? You can represent it by a sphere. This is called Bloch Sphere. Or like arrows and going up or going down. Going up because it's really pointing to state 0. Going down because it's really pointing to state 1. Pero pagka arrows lang, you don't really know where the position is of that state. Ngayon, if you talk about positions and everything, sa Bloch Sphere, kompleto. Meron kang x-axis, may y-axis ka, baka may z-axis ka. No? The state 0 is located on the top of the Bloch Sphere. State 1 is at the bottom. So, madali na matandaan, no? So, pag ito-drawing mo yan sa classmate mo o sa klase mo, ang hirap mo i-drawing lahat yan. So, ang ginagawa ko lang is drawing ko yung isang buong sphere. Pagkatapos, maggagawa ko ng isang parang ano dyan, yung what you call that, that divides the earth, equator. Tapos, yung center na yan, you start drawing the arrows like that, mas madali. Ito is like towards that, no? Okay? Okay. Ngayon, ito na yung mga i-move natin yung ideas ng quantum mechanics na main ideas kanina to quantum computing representation. So, I am talking only about Bloch Sphere here. Mamaya, we can talk about the gates. Okay? So, remember what is this? Superposition Bloch Sphere. So, a superposition can be equal, meaning that it contributes equally to the state. No? Sa superposition kasi, pinag-uusapan natin na 0 and 1 are present at the same time. So, paano natin i-represent yun sa like this thing, no? So, makita mo here, this one arrow here is halfway between state 0 and halfway also on state 1. If the arrow is here, you know that half of it is 0 state and half of it is like 1. It's 50% state 0 and 50% state 1. Ito naman, it's very near 0 state. No? In fact, it's approximately about 80% very near 0. And what do you expect? If it's at 80%, then the state 1 is only 1%. This one is pointing to very near the state 1, which is about already 80% state 1, and the rest, of course, is 20% state 0. So, ngayon, pagka ginamit mo yung Qiskit, magandang i-drawing niya kasi makikita mo mag-animate yan. No? Pero when discussing it like this drawing will suffice. Okay. Because we borrowed a lot from quantum mechanics, we are also conforming to how quantum mechanics formulations or writing things in quantum mechanics, we bring that knowledge to quantum computing. Kaya kailangan natin mag-aral ng quantum mechanics na basic. No? So we're lucky that we have a theoretical physicist here, si Bobby, who's really adept on it. No? I'm a guy that who would like to bring it really to a level of technology, and I can make it work on a optical table. So because that's instrumentation physics. No? So we have what we call ket notation. The ket notation is used to represent the state of qubits. So if we say that we want a qubit that is 0 state, okay, it's an arrow going up, and we write the ket as 0 between the symbols. Ito sa computer, key lang itong ginamit ko sa computer. It's I don't know what characteristics, but it's a long vertical bar very near the return key. No? And then you have it's like a greater symbol, no, greater than this one symbol, but actually you put that and you put 0 there and you represent a 0 state. This one, it's pointing down. You know that in a Bloch Sphere, it's 1 at the bottom and this one is 0 state at the top. And you have to write it this way. You have a 1 and that is enclosed here. Paano kung superposition? Hindi naman sila sa taas, hindi naman nasa baba. O parang pinagsama lang yung arrow na nasa taas at saka sa baba, and a superposition of 0 and 1. You have to remember that a superposition is between 0 and 1. 0 and 1 state, palagi yan. No? Pag napunta sa 0 lang yan talaga yung value niya. State 0 lang yan. Diba? Pag napunta talaga sa 1 yan, state 1 lang yan. But anything between there, we should be superposition. Ngayon, because the line is actually locus of points, it's actually locus of points, you can have so many positions, superpositions anywhere between state 0 and 1, so many. Because it's an infinite number of points here. So, ang daming state na pwede mo talagang magawa. No? That's one key in quantum computing. Okay, now, we go to the gate. If you don't remember anything, any gate at all after this talk, you just remember the letter X. And you remember your first gate. X gate, no? So, the operation of the X gate gives the opposite of the input. Bakit opposite? Kasi, nag-start siya sa 0, and for purposes of initialization, in quantum circuits, everything has to be started with a state 0. Sa initialization na, para mag-simulate. Okay? That will ensure you a good propagation of signals on those gates. So, this is going to be 0 because look, in the Bloch sphere, the arrow points on the top of the sphere. Pag dumaan sa X, what happens? Oops, pupunta yan doon sa state 1. That's the effect of a X gate. Okay, paano naman kung halimbawa start ka sa state 1 and it goes to an X gate? Oops, pupunta yan doon. There is no other way but to flip it from 0 to 1 or 1 to 0. It cannot be in between because if it's going to be in between, it's called superposition. It's not an X gate. Okay? So the X gate results to a 180-degree rotation about X. Okay. Next gate. It's called H gate or Hadamard gate. If X gate changes the state from 0 to 1 and 1 to 0, the Hadamard gate, don't do that. Actually, what happens is that it gives you a position anywhere between like 0 and 1. No? Okay, so again, if we start with an initialization of 0 state, ano mangyayari? If you start with a 0 state and you input that to a Hadamard gate, it will go to the positive. The positive is on this part, the negative is on this part. Okay, if you start with a state 1 and you input that on Hadamard, it will go to the negative. This part is negative here. So, paano naging superposition yan? Hindi naman direktong dumiretso sa 1 eh. Hindi, dumiretso sa 1. Kundi, it lies between 0 and 1. Input 1, it lies, this one lies between 0 and 1. Now, this one lies between, from positive to negative, nandoon, sa kabila napunta. Now, it seems to be very simple graphic, di ba? Pero once you start programming in Qiskit, this can be confusing, but you have to have a very good mental picture of things so that you will remember this when you're actually writing a code in programming. So you have to have a mental picture of this one. So the Bloch sphere is your mental picture. You don't do programming so that you all do the Bloch sphere in the code there, no? And then let's give you no. So okay, now we now have X, we have now H. Now we have the Z gate, Z gate. So ano naman ang ginagawa ng Z gate? So input state 0, dumaan sa C gate. Ang nangyari ay what? Oh, bumalik ata sa dati, di ba? At ganon, di ba? Ito. State 1 and then it goes to negative 1. Ito. From plus, it becomes negative. From negative, it becomes plus. The Z gate is a 100-degree rotation around the Z axis. Yan ang differential niyan. So you have seen where's the Z gate, di ba? C axis, di ba? Along the poles, di ba? Okay, yun naman yun. Okay. Now, there are very specialized gates that you need so that you can quantumize or put a quantum mechanical idea like interference to make it happen on a quantum computer. No? Or the idea of paano ko gagawa ng entanglement, no? Alam ko, inaccept ko na yung quantum mechanics na may entanglement, pero paano ko gagawa ng program mag-entangle? So you need this kind of gate. It's called controlled X or CX or C naught. It's a 2-qubit gate that follows these operations. Ang input niya palagi dalawa, isang starting bit 0 and then a second bit 1 here. Yung isa pang control, yung isa pang target. So whatever is input here, ipapasa niya yan dito pag nasatisfy mo yung Q0 dito. So if the qubit is 0, do nothing to the target qubit. Pag 0 yan dito, do nothing. Pero pagka naging 1 yan, ano mangyayari? Apply X to the target qubit. Alam niyo X, di ba? Alam niyo X, di ba? Ang effect. Ngayon, if you place a Hadamard gate before this control qubit, this C naught, you'll create an entanglement effect. So the ideas of quantum mechanics, that things like superposition, entanglement, discreteness probability is realized in a quantum circuit. And then that quantum circuit is used to program the quantum computer. So that's why kailangan natin ng quantum mechanics para maintindihan natin paano gumamit ng gates na to. Diba? So makita nyo, that's the case. No? Kung gusto mo nang karoon ng entanglement and superposition, Hadamard kailangan mo at saka C naught gate. We will do more on this one pag napunta na sa exercise. No? Okay. Isa pang example pala to, no? Na doble ata. But it's the explanation. Okay. Now, alam na natin yung mga gates, ang input and output, pero at the end actually of a programming code or a programming routine, you also need to measure the absolute, or meaning the classical, the real output. The classic is called the classical output. Ngayon, sabi ko nga kanina that once you do the measurement, once you observe, all the quantum system collapses, all the superposition collapses, and gives you a single value, which is a classical value. Isa lang bibigay sa'yo, and it's a probability. No? So, in general, the quantum circuit model captures 3 major parts in a quantum circuit. Una sa lahat, what the quantum states ang input mo, yung gates na ginamit mo, and then measurement. So pag titingnan natin ang sequence of things, sa code mo dapat, okay, ano kaya yung i-input ko? Q0, ano ko? Yan, 0 yan. Tapos papasok siya sa X gate. Ano mangyayari doon pag 0 tapos X gate? Okay, ano mangyayari doon? Tapos kakabitan mo siya ng measurement, tapos magbibigay siya ng, pag niran mo yung program mo, magbibigay siya ng measurement. Magko-collapse yung quantum system, bibigyan ka ng classical information. Okay? No? So, ganun din dito, no? Pumasok yung 0 sa Hadamard, tapos nag-measure ka. In A, this part, X gate changes the qubit from state 0 to state 1. It will be always 1, hence it is predictable. Kasi maski anong gawin mo, the state 0 pumasok sa X gate, magiging siyang state 1. Diba? Yun ang function niya eh. Pag sinukat mo yan, at nakakuha ka ng 0, problema yon. Hindi gumagana yung X gate mo. Dapat 1 ang ibigay sa iyo kasi X gate yan eh. Pagka ang starting na quantum state mo 0, dapat 1 ibigay niyan. Pag program na simulation mo, dapat 1 ang ibibigay niyan. O kung Hadamard naman, dapat superposition. Okay? So, that will give you 1. Kung ito, it's like dice. It can be anything because remember that it is between 0 and 1. Anything there can be anything. Nilagay ko lang dyan dice. No? So, it's truly random. But that's my point. Okay? Okay. Now, this is a little bit of math, but I'm sure that our friend here will explain it more. But I'm just showing there paano yung sabi amplitude ng state. So, for example, we have a ket notation here, di ba? Makita nyo na, okay? Normally, papakita sa inyo ket notation 0 kasi ito talaga ang expression nun. Ngayon, may amplitude dun sa this particular qubit. This one, So may amplitude din. If that's 0, it will be 0 yan, di ba? So ito, magiging what? Ito rin magiging state niya. So kung halimbawa na dito, alanganin siya, ito 0. Okay? Alanganin ito. Kasi sinabi dito, it's about 70% 0. Oh, tapos 30%, siyempre 100% naman lahat. Eh yung 1, magiging na lang siyang 30%. Pero kinuha niya yung value, kinuha niya yung square root na yan. Okay? Getting the square root is also like getting the effective value. Okay? So yung 0.70 na yan is because you're saying that this is about 70% 0 and then it's like 30% 1 here. 30% yan kasi ano na yung 7%. Yan ang magiging tunay na amplitude niyan. Ito magiging tunay na amplitude niyan. Ngayon, pag nandito yung arrow mo, nasaan yan? Positive x, di ba? Positive, which is this one, positive. Makita nyo is 1 over square root of 2 and then state 0 plus 1 square root of state 1. If you actually get the square of this 1, this 2, magiging lang siyang 1 half, di ba? So 1 half, kalahati 0, kalahati 1. Di ba? Kalahati yan, no? Kalahati yan, kalahati between 0 and 1. So pag kinuha mo yan, kunin mo yung absolute niya, kunin mo yung square root niyan. And then kunin mo lang square value niyan. Okay. We're actually done and I'm just going to tell you about when you start coding to use this cheat sheet. Okay? Bibigay ko naman sa inyo yung slide na to and then you'll start coding. I'm sure that Asher will teach you how to do the IBM Meet, but I can just show you some basic of it later. But okay, so for example, if you just want to create a quantum circuit with a qubit 1, i-type mo lang yan sa Python lang to, Python yan. Okay? It uses Python. Sa loob ng sa loob ng IBM Media na sa loob ng IBM Qubit, IBM Quantum. Sa type mo lang yan. QC equals quantum circuit. Take note of Q is uppercase, C is uppercase, then open close parenthesis 1. That will create you 1 qubit. Now, if that's n, you have 10 qubits, n equals 10, put mo lang yan 10. Or like you have n qubits na quantum yan and then m classical bits, meaning like how many binary bits you need. Okay, yun yung ganun kasimple ito, no? And then if you want to create a quantum gate, you can use, for example, X gate on qubit 0. O ayan, bibigay mo QC dot yan na. Or index the A, Z, H, etc. Z is free gate and then Hadamard
Hello, Burns. We cannot hear you. Jabez, are you able to hear Burns?
Not on my end, po, sir.
Burns, you might need to restart your sound.
Okay. So ibibigay ko rin mo sa inyo slides na to, but I'm just guiding you through very quickly paano ka mag-set up ng IBM Quantum account. So normally, pupunta ka sa website, yung IBM Mid account. Yan, nakasulat dyan, quantum-computing.ibm.com. Bibigay sa'yo yan. Yung UN na yan. And then, i-click mo lang yan, kasi naka-register na ako dito. And then you can actually launch it kung may account ka na. Pag wala, you simply have to, sign in, new to IBM, create an IBM account. Madali lang talaga to. Mas maganda kung if you use university email because they reply very fast. O kasi pang university. Okay, tapos pag meron ka na, i-email lang sa yan, tapos and then you can see that may mga programs ka na dyan, kung din pa. O, tapos itong gagamitin mo, IBM Quantum Lab. This one is like a lab that I did for Qubit in week 10. So I have here parts the the needed files needed for Qiskit. Tapos ito yung mga files ng projects dito. Tapos andyan ito yung actual na, let's say, I'm going to actually run it on the actual computer. Hindi lang simulator but back-end, ang tawag doon back-end. Pinakita ko lang dito that ginagamit kong back-end yung Manila. Ang nakapila dyan, 26. Ang dami. So that means if you run your program and on a real back-end, that will not give you like the speed of your laptop right now. It will give you 2 weeks later as an answer. Because why? 5,000 Indians are queuing on that computer. So naka-queue ka dyan. 2 weeks yan bago makuha. So better, if you're just testing the code, you use a simulator instead. Okay? Simulator lang muna. Okay? But if you want experience, why not? Kaya lang matagal ko talaga yung resulta Sobrang tagal. For example, how many qubits and configuration. Oslo is that particular circuit to execute that. And then this one is running on an actual hardware. Ito yung code ko sa qubit into classical 2 qubit input, 2 classical bit output. Alam niyo na yung syntax niya, binigay ko sa inyo sa cheat sheet. Alam niyo na rin yung QC.H, meaning initialize yan sa Hadamard. Gumamit ako ng CNOT gate. And then I said, I'd like to measure this. Using this binary and qubits, and then I'd like to draw the circuit. Ito yan. And then what job is this? So yun. This one goes to the quantum computer. It has to be transpiled. It's called transpiled. Hindi compiled, kundi transpiled. And that's going to be executed by the quantum computer or a quantum simulator then. And you'll see the result is really a probability. Output is a set of probability for 2 qubit circuit. So 0011, ang probability niya 549, 475. Parang it's not so exciting, di ba? Pero it is really already giving you the execution of all these underlying quantum mechanics on that machine. Okay, it's another exercise. For example, this one is H on qubit, X on qubit, etc. So these are some of the also the references I used, and then I reference this one for my content. Okay, that ends my talk. So anong oras na ba? Tumama ba ako sa oras? Okay. Do you have any questions? Hello?
Hello, boys. Thank you. Javas?
By the way, I need the Jabez, if you can send me the emails of the participants, because I'm going to give them a exercise sheet.
Okay po.
And also I'm going to give this slide to them. Maski tomorrow. Ngayon, if there are among you that needs clarification, you can just write me email, no? Chavez would know my email, burns.buenaobra@gmail.com. Okay, so baka naiya magtanong, baka pwede nyo lang i-chat or what, or kaya itanong sa email. Pwede rin. So I think Elmer would be doing a little more deeper on especially on the analytical side. I am the guy who would like to transition you from very, very sophisticated math of things to actually be able to program the quantum mechanical effects that you wanted to be executed on a quantum computer. So but again, these fundamentals are necessary. The things that Bobby teaches, in the course is also very necessary. Also, the fundamental by Elmer is necessary. Okay. So many young people here. So ayan. Meron ba tayong tiga-MSU rito? Umattend? Okay. Ah,
Okay, if you have any more questions to Sir Burns, you can send them through Discord or you can send him an email. So we'll share his email then on later.
or we can have a group chat if you want, no?
Yes, po. All right. Okay. Yeah, you can just send your questions on Discord, pero for the sake of time, so at this point, we would like to move forward to the second session for tonight. So I would like to call on Sir Elmer for that part. Thank you po, Sir Burns. Have a
Yes.
great night po. Hello po, Sir Elmer.
Hello, am I being heard?
Yes po, loud and clear.
Yes.
Let me just share my screen. Thank you, Jabez, and thank you, Sir Burns, for that fantastic presentation. Let me just share my screen. Okay, so yeah, good evening, everyone. I'm back. I hope you're not tired seeing me because this is actually my third lecture on this series, and I would like to commend Sir Burns for that fantastic introduction on the quantum computing concepts. Like what he mentioned, I will be discussing some of those things that he had already discussed, but on a more mathematically rigorous. Sorry, we have different approaches. So he actually introduced you to the fantastic concepts in quantum computing. So this time I'll be discussing quantum gates, but just a heads up, this is going to be just like the first lecture. Sorry, there's a lot of math in here, so just brace yourself. Okay, so outline, there's going to be a math review in classical versus quantum. So I think Sir Burns already shared with you some of the differences between classical approach and quantum approach to computing. Then it's also important that I have to reiterate the concept of qubits and superposition, although Sir Burns have already discussed them in the previous lecture. Also, the concept of Bloch Sphere. But the meat of my lecture will be on quantum gates. Okay, and at the end of the slides, I'm going to give some key takeaways. Okay, so review of the matrix multiplication. I'm sure you already know this. So basically, you can see here from the examples that I have shown here on the screen, it's just this row by column linear combination. So you take x sub 1, you combine it with a, and then you add the combination of y sub 0 and y sub 2. I'm sure you already know this. I've already discussed this with you in the first lecture. Representing classical bits as vector. So Sir Burns mentioned to you about the Dirac notation. So this one, we can also represent, for example, a bit using a Dirac vector notation. For example, the 0 here, 1, 0, and the ket 1 here is 0, 1. So in quantum computing, we call this the computational basis. You're going to see a lot of this ket 0 and ket 1 in the succeeding slides. Operations, I just would also like to review this operations on classical bit. So we have here, so if you have a classical bit, we can actually do some transformation on those using by matrix multiplication. So we have here, for example, the identity. So think of it, it's just like a function that you have an input and then you have an output. That's why they call it gate, because in a gate you enter something and you enter a gate and then you become something else, something like that. So that's sorry for my poor analogy, but in classical bit we can also do we also have some operations. So we have here the identity. As you can see here, the identity does nothing, so I call this the lazy gate. And then the negation basically changes the bit from 0 to 1 and from 1 to 0. And then we have the constant 0 function, or this operation is just for it doesn't really care about the input. The output is always 0. And constant 1, same thing, it doesn't really care about the input. The output is always 1. So here are the as you can see, these operations can be represented as matrix vector multiplication. So if you multiply a 2 by 2 matrix by a 2 by 1 vector, the resulting product is a 2 by 1 vector. Okay, so these are just a review. So I cannot emphasize enough the importance of comparing classical computing to quantum computing. So here's the tip. In order for you to, I mean, just a motivation, the best thing to understand quantum computing is somehow you should understand how classical computing works, because basically it's really hard to appreciate the concepts in quantum computing if you don't have any familiarity with classical computing concepts. So last time we talked about the complexity of algorithms. So that's very important. And we also talk about the different logical operators used in classical computing. So in classical computing, states are bits or 0 and 1, and gates are Boolean logic operators. So you have here 0 and 1 is 0. Sorry. Yeah, 0 or 1 equals 1, and this is the negation operator, not 0 is equals to 1. So in quantum computing, states are vectors, as we will see later, and we can visualize that using the Bloch sphere. Gates are matrices, okay? Gates are matrices, remember that. So it just means that when you want to transform the state of a qubit, you just multiply that vector. That state of a qubit is represented by a vector. So multiplying a matrix to a state vector, it just changes or just transform that vector. Superposition, yeah. When a qubit is in a state other than ket 0 or ket 1, we say that it is in superposition. This has already been explained by Sir Burns a while ago. The qubit is in some sense both of 0 and 1 at the same time. So for mathematically inclined, superposition is just a fancy term for linear combination. And linear combination, I have already discussed that in the first lecture. Okay, representing qubits as a superposition of vectors. As you can see here, any qubit state can be represented by this ket psi. Think of it as just a variable that we represent any qubit. So any qubit ket psi, this Greek letter here is xi, sorry, or psi is equals to alpha times ket 0 plus beta times ket 1. So ket 0 and ket 1 are our computational basis vector, okay? Meaning we can represent, since this is the basis, it can generate different kinds of, or different linear combinations in that vector space by multiplying it by this alpha and beta, or this is just a linear combination or a superposition, meaning that this ket psi is a superposition of this ket 0 and ket 1, and alpha and beta, these coefficients are called the amplitudes. Okay, when you get the absolute value of and another constraint that we need to be aware of is that in order to label this as a valid quantum state, it should satisfy this condition. So this condition, or the normality, is called the normalization, or the normality condition, meaning the amplitude, the square of the absolute value of the amplitude plus the square of the absolute value of the amplitudes, the sum of them must equal to 1. Okay, so if this is the amplitude, this represents now the probability. Okay, probability of, for example, if alpha, when you get the absolute value, you square that, that will represent the probability of getting a 1 when this quantum state collapses to a deterministic bit. Like, for example, so alpha squared here, or the absolute value or the norm of the alpha here squared represents the probability. Same with beta. Since these are probability, they should add up to 1. And mind you, these are alpha and beta are complex numbers. Okay, so these are the other important qubits, qubit states. This one is ket plus. This is a superposition between the sum of ket 0 and ket 1, then ket minus. This is the superposition of the difference between ket 0 and ket 1, and then ket I, the absolute value. This is a superposition between ket equal superposition. Sorry, I should mention that equal superposition, because this is 1 over the square root of 2. And when you square that, okay, it will give you 1/2. Okay, so that's why I should say equal superposition. So, and then you have here the ket negative I, which is represented by this expression. Okay, so you can see here, all of these can be represented as a linear combination of ket 0 and ket 1. And okay, as you can see here, this one is a scalar. So this one is a sum, so vectors of 2 vectors. So initially this will be, if you want to a more succinct representation, so this is the representation of this one when you add them together. Okay, so this is for this one, this is for this one, and this is for this one. So these are all qubit states. These are important qubit states, as we will see later, because they can be represented as poles in the Bloch sphere. I'll show it to you later. But there are other qubit states, because as you can see, there are infinite number of qubit states. This one is also an example of a qubit state. The important thing here to make it a qubit state is that we need to satisfy this. Okay, this equation. So in this case, the alpha is 2/3 and the beta is 1 minus 2i 3. So if you get the, so last in the first lecture, I think I discussed with you getting the absolute value of a complex number, or getting the modulus or the norm of a complex number. So this one is just the absolute value. This is a real number. So this one is easy, pretty straightforward. So just 2/3 squared. So that's going to be 4/9. But this one is not that straightforward. So getting the absolute value and the squared. So the absolute value of this is actually 1. You have to multiply this by its complex conjugate, okay, to get the absolute value, and then you square that. So that will result to, see, this is 4/9. I think this will result to 5 over, sorry, this is 4/9. So this should result to 5/9. And this one is also an example of a qubit states, and also this one. As you can see, these are all expressed as a linear combination of the computational basis ket 0 and ket 1. This one is also a complex number in exponential form. So all of these are example of qubit states. Now, to give you an exercise or assignment, can you verify that these are actually qubit states? So how can you verify? You get the value of alpha and beta and check whether the squared of their the squared norm, the sum of their squared norm is equals to 1. Okay, so that's going to be your assignment. Next, okay, qubits on the Bloch sphere. So Sir Burns introduced the Bloch sphere. So all of the qubit states can be represented as a point on the Bloch sphere. So the Bloch sphere is actually a unit sphere, meaning the value of r So all of these are complex numbers, right? So the value of r is equals to 1. So it just depends now on the theta, or if we call that the before we define the theta, we should define the axis first. So we have here the z-axis, the y-axis, and the x-axis here. And the theta is measured an angle from the North Pole, okay? So conventionally, we have here the North Pole, and then the theta is an angle measured from the North Pole to down from the North Pole to the other pole. So that's going to be, and it ranges from 0 to pi, or 0 to 180 degrees. And then you have another parameter here, the phi, or the phase. The phi measures the angle across the x-axis. So this, the phi only rotates with the on the xy plane. So it's called the azimuthal angle. And the range of phi is from 0 to pi. Basically, if a point in this sphere is in this unit sphere is a quantum state. So, and based on the previous slide, the quantum state is equals to the alpha times ket 0 plus beta times ket 1. By the way, ket 0 is located here. So this is a pure this is the ket 0, and then on the south pole you have the ket 1. So any point here will just be a linear combination of these two computational basis vector. So ket psi is equals to, so if you're going to represent, the a quantum state or a qubit state in terms of theta and psi, this is the equation. You can find the book that can actually derive this. But the important thing here is you're just you can just parameterize, or you can just represent any quantum state in terms of the coefficient here, or in terms of the amplitude, or you can represent it in terms of the angle, the polar angle and the azimuthal angle on the Bloch sphere. Here alpha, but if you can, if you want to change from one parameters to another, for example, from angles to amplitudes, these are the formula. There's a nice derivation. You can find a lot of books that can derive this formula here, or this equation here, but I will not do it here because due to lack of time, and I did not include that on my slides. So yeah, Bloch sphere is a unit sphere in a spherical coordinate system. So going back to our math class or analytic geometry, we can represent a point in space using the Cartesian coordinate, for example, in a 2D plane, the Cartesian coordinates. So that's being represented by the horizontal axis, by the location, the horizontal axis, and the vertical axis, the coordinate along the horizontal or the vertical axis. So you have the x, y. But that same point can also be represented in terms of the length of that point to the origin and some angle along the horizontal axis. And now that's actually polar coordinates. So polar coordinates is represented by r, the radius, and theta. But in 3 dimensions, I think the 3 conventional way of representing a point in 3 dimensions, you can use the Cartesian, which is just x, y, z coordinates, or you can use cylindrical coordinates. So in that case, you're going to use 2 distance and 1 angle. But you can also use the spherical coordinate system. But this time, you'll just use the r, the length of that point, and then the 2 angles, in this case, theta and phi. But since we're just using a unit sphere, so all values of r is equals to 1. So we will just limit ourselves to a value of r equals to 1. So basically, our degrees of freedom will now be reduced to just 2, theta and phi. Okay, so that's going to be our Bloch sphere. So Bloch sphere basically, by the way, you can compute for the value, or you can change from one coordinate system to another. Like for example, if you want to go back to the Cartesian, this is the formula. Given theta and phi, you can compute for x. Given theta and phi, you can compute for y, and also for the value of z. So that's the formula. And going back to the Bloch sphere, these are the 6 important states that I've shown you before. So in column vector representation, ket0 is this one, ket1 is this one, ket plus is this one. It's 1 over the square root of 2, 1, 1. Okay, so I've already shown this to you a while ago. Okay, and these are 4. So these are important states. Why? Because we can actually label the Bloch sphere in terms of important poles. Like for example, the North Pole is your ket0, the South Pole is your ket1, and along the equator, you can determine the plus here. For plus and minus, this constitutes your x-axis, and then negative I and plus I, this constitutes your y-axis, and this is your z-axis, your 0 to ket0 and ket1. From ket0 to ket1 is your z-axis. If you're going to get the cross-section of this one in the across the along the equator, if you're going to get the cross section of the Bloch sphere, that's basically your Argand diagram or your complex coordinate system, wherein you have the y-axis as your imaginary unit and then your x-axis as your real unit. So basically, that point there is just a complex plane, the complex plane. And you can see here the different angle representation for the ket0, since this is your theta is equals to 0, so it hasn't been rotated. Your phi is also 0. For ket1, so here is ket1. So your theta should be from here to here, so that's already pi or 180 degrees. But your phi is 0. And for ket plus, all of these, as you can see here, are all pi over 2, meaning their theta, all of these are along the equator, okay, along the equator. And then for the different values of, so if this is your 0 for phi, so for plus I, this one, so your phi has rotated 90 degrees. And then if you rotate again 90 degrees, it will go to ket minus. If you rotate again to 90 degrees, or that is equal to 3 pi over 2, it will go to ket negative I. So I hope you visualize the important points on the 6 important points on the Bloch sphere. Locating a qubit on the Bloch sphere. So this is also important. Like I think Sir Burns mentioned this a while ago. So once you already have those important locations, you can somehow visualize, for example, an arbitrary qubit state, like for example, this one. You can somehow locate where or can estimate where this qubit is. Like for example, is it above the equator? Or if it's above the equator, is it in what quadrant? Okay, so basically those are the things that you need to somehow you can visualize based on a given qubit state. Like for example, so you can do that based on the formulas that I have already shown you. We have how to convert angle at the theta and the phi in terms of the alpha and beta. So basically, this is your alpha, right? And this is your beta. So you have the formula, then you can actually compute for the theta and the phi, or the azimuthal angle and the polar angle. And by that, you can now somehow locate the qubit on the Bloch sphere. Okay, so you can actually locate that and using those formula that I've shown you. So can you locate the following on the Bloch sphere? Like for example, this qubit state. Where is that on the Bloch sphere? Is it above the equator? Is it below the equator? And where is it nearer? Is it nearer ket0? Is it nearer ket1? Or is it nearer ket I or ket so? Those are the things that somehow, based on some computation, you'd be able to find out. So this is going to be your assignment again. Can you, or your exercise? So can you locate the following on the Bloch sphere? So these 3. So I'll be, Jabez will also be sharing these slides with you. So these are the exercises. Operation on qubits. Okay, how do we operate on qubits? So the same way we operate on bits with matrices. So matrix operators. So basically, the operation here is matrix and vector multiplication. As you can see, A vector represents a qubit state. A matrix represents a gate or an operation. So in this case, this is a matrix and this is a vector. So a 2 by 2 matrix multiplied by a 2 by 1 matrix will result to a 2 by 1 vector. So basically, it's just the matrix operation is just somehow transforming that vector or somehow changing the qubit state. Okay, so there are several important matrix operators which only make sense in the quantum context. Now, let's go to the meat of the discussion. So what are quantum gates? Quantum gates act on qubits like logic gates act on bits. So a quantum gate transforms the state of the qubit into other states. As you can see here, this is 1/2 and then square root of 3 over 2. Now, when you multiply it with this matrix, it becomes square root of square root of 3 over 2 by 1/2. As you can see, kind of swap it actually swap the bits or the components. So we will be dealing with a lot of those different transformations. So quantum gates, but there are important properties of quantum gates. First one is it should be a linear map or a linear transformation. And the other one is the total, it should preserve the total probability equal to 1. For example, if there is some transformation that will result to, when you compute the probabilities, the sum of the probabilities, it will probably go outside 1 or not equal to 1. So that's another constraint here. So the first constraint is it should be a linear mapping. The second constraint is it should preserve the total probability or the normalization constraint. So we represent U here as a quantum gate. So basically, U is just a variable for a quantum gate. Okay, a variable name. Now, U is very significant because later on, when you go to to linear algebra, it's actually just unitary matrices. I will not discuss what a unitary matrix is, but there's a significant correlation between quantum gates and unitary matrices. Okay, so U multiplied by KED0. So for example, this one is its representation. So U KED1, so 1/2 of this KED0 plus square root of 2 plus I over 2 KED1. So let's check. So property 1, a quantum gate must be linear, or meaning we can distribute it across superposition. So that's what a linear mapping does. Okay, when you say linear mapping, we can distribute the gate. Like for example, here, this is your gate, and this is your quantum state. So basically, when you say it's a linear mapping, it satisfies this equation or this. So you can distribute the U inside for each of the component of the quantum bit. Okay, so U times alpha KED0 plus beta KED1 is equals to alpha U KED0 plus beta U KED1. Okay, so let's check here. So alpha times U KED0 plus beta times U KED1. So in this case, it actually preserves this linear, it actually satisfies this property. Property 2, the total probability must remain 1. So let's compute for the total probability. So the total probability is just the squared of the absolute value of each of the amplitudes or your alphas and betas. So this is the computation. So the bar here represents the absolute value or the modulus, and then you get the square of that. If it's a complex number, you have to multiply it by its complex conjugates. Okay, and you will see that basically. So I'll just be sharing this. You can check the computation here. But when you perform this operation, it will lead to 1. So that verifies that this is U is a valid quantum gate. So that's the two things that you need to check whether a transformation or is a valid quantum gate. Reversible computing. So reversible means given the operation and the output value, you can find input value. So for example, AX is equals to B. Given B and A, you can uniquely find X. So that's what reversible computing means. So operations which permute are reversible. So operations which erase or overwrite are not reversible. So we think of it like you have matrices, and some matrices doesn't have inverse, right? But some matrices they are called singular, okay? But the important thing are you need to find matrices that are non-singular or invertible matrices. Another thing in terms of functions, think of functions at there are some functions that are not one-to-one and onto, okay? Meaning the inverse is not a function, okay? So it's somehow related to this part. And the important thing is operations which permute are reversible and operations which erase and overwrite are not. So we have here the identity and negations are reversible. Constant 0 and constant 1 are not reversible. Quantum computers use only reversible operations. So we will only care about those reversible operations. Example here that I've shown you before, identity and negation. These are reversible operations. If you know that it's an identity, you can, based on the output, you can know you can know the input. Same here with negation, you just have to swap. But constant 0, for example, if this is this is 0, this is ket 0, right? This is ket 0. But once given a ket 0, if this is the function, you cannot know what are the inputs. Is it ket 1 or is it ket 0? So these are not reversible operations. So constant 1 is also not reversible operations. Reversible gates. So classical logic gate is reversible if its outputs are unique. So a gate with input A and output B. So remember, A is input, B is output here. Okay, with the following truth table is reversible because it's just, as you can see here, 0 becomes 1, 1 becomes 0. So that's the gate, that's the following to a bit. From 0, it turns it to 1. From 1, it turns to 0. So on a qubit, you have here, for example, this is your quantum gate. Quantum gate acts on ket 0, it becomes ket 1. Quantum gate acts on ket 1, it becomes ket 0. As you can see, testing for the linearity of this gate, as you can see that it is linear. It was able to distribute the beta and alpha. It's still a valid quantum gate. And testing for the normality, if it's normalized, you can see it's just swapping. Basically, it's b squared, the absolute value of b squared plus alpha squared is also the same as alpha squared plus b squared, and it's equal to 1. So what happens here is you're just swapping the bits. So this is an example, a valid quantum bit. How about this one? Let's consider this truth table, 0, 0, and then 1, 0. This would act on the basis. For example, if you have this gate, 0, it always turns to 0. But when you check for the linearity, you can see here, based on this computation, that from here, what happens is that since this beta ket 1 is equals to beta ket 0, because it's always changing. If you apply the gate, it's always changing that quantum state to 0. So it will become this. So basically, it will just be alpha plus beta ket 0. So meaning the ket 1 disappears. Okay. So checking for the normality, you can see here if you get the squared absolute value of the amplitudes of this, it will not be equal to 1. So you can see here, when you get the squared of this is equals to alpha squared, norm of the alpha squared plus norm of the beta squared plus the complex conjugate of alpha times beta plus the alpha times the complex conjugate of beta. So this will not be equal to 1. So this one, as you can see here, this one is not a valid quantum gate. So it's also important that quantum gates are reversible. So for exercises, you have to do this A, B, C, and D. For each of the gate, for each is each gate a valid quantum gate? So you have to check the two criteria. The first one is linearity. The other one is the test for normality for each of these truth tables. Okay, for the truth tables that are the gates that signify represents this truth table valid. So you have to do the checking for the linearity of the gate and the normality. Okay, so this is the important part of this lectures. I'll just be enumerating the important 1 qubit gates. Okay, 1 qubit gates. The first one is called the identity gate. So identity gate turns ket0 into ket0 and ket1 into ket1, hence doing nothing. So this is the lazy gate. So it just, when you apply it, nothing happens. It's still the same. So it's represented by this matrix, identity matrix. Okay, and next is the poly X gate. So this is the X gate that Sir Burns mentioned. It's actually the swap gate or the NOT gate. Basically, if you apply the X gate to ket0, it will turn to ket1. If you apply the X gate to ket1, it will be turned into ket0. And this is the matrix representation. Okay. So you already have this ket1 and ket0, right? So these are just vector. Now, try multiplying this matrix to that vector and verify that indeed this is the case. Okay? For this one, this is very trivial because identity matrix, you already know based on your algebra that whatever vector you multiply with identity matrix will result to that. But this one is kind of reverse. So try multiplying this with a vector 1, 0, and then another one. This matrix, multiply it with vector 0, 1. Okay, this is 0, 1, and this is 1, 0. Remember? Okay, another thing to observe, x squared is equals to I, meaning if you do it twice, if you multiply this twice, okay, or if you multiply x by x, it will just be result to 1. Okay, and by the way, this polygate, there is a geometric interpretation on the Bloch sphere. So basically, this is just when you apply the poly X gate, it's just rotating the Bloch sphere. Basically, if you have rotating the Bloch sphere 180 degrees, okay, or pi by pi radians amount, 180 degrees. Okay, along the x-axis. Okay, that's why it's called the X gate because it's rotating the Bloch sphere along the x-axis. Meaning, if you have a point here, when you rotate it 180 degrees, it will become a point on the, like for example, if you have a point in this hemisphere, if you rotate it to the 180 degrees, it will now be a point on the other side of the Bloch sphere. Okay, so that's going to be a different representation now. So that's effectively the interpretation of multiplying by the X matrix or by or the effect of the X gate. And as you can see, if you do that twice or multiply X, you operate on it another time, so you're going to just go back to the same location. It's because you have already rotated that 180 degrees, and if you rotate it again, if you apply the same operation again, it will just go back to the same position. That's why you end up with the I or identity matrix. As you can see, you can verify that it will just be a repeated pattern. So x raised to the 1000. So this is an odd number. For every odd number, it will just be equal to x. For every even number, it will be equal to the identity matrix. Okay, so x raised to the 1000 is just x raised to the 1000 times x. But as you can see here, x raised to the 1000 is even number. So that's just I multiplied by x. So it will become x. So remember that. So if it's an odd number, if the exponent is an odd number, it will be equal to x. If the exponent is equals to an even number, it will be equal to the identity matrix. Okay, the poly Y gate, this is the representation of the poly Y gate. Y applied to ket is I multiplied by the 1, and then Y applied to the ket 1 is just negative I times ket 0. You can verify that by using this matrix representation. So you multiply this matrix to a ket 0 and see what will happen. As you will see, you will end up with this state. Okay, same thing here. If you multiply this matrix to a ket 0, for example, in this case, ket 1, sorry, ket 1 is 0, 1, right? 0, 1. So you multiply that, you will end up with this expression. Effectively, that means that on the Bloch sphere, if you have a qubit state on this, you are going to rotate that across along the y-axis 180 degrees. Okay, so that's why it's called the Y gate. Next, the poly Z gate or the Z gate keeps 0 to 0 and turns 1 to negative negative of ket 1. Okay, negative of ket 1 is just 0, negative 1. Okay, negative of ket 1 is 0, negative 1. And this is the matrix representation. So basically, if you multiply, if you apply Z gate on the ket 0, it will not change. If you multiply ket Z with ket 1, it will be equal to the negative of itself. So basically, you use this matrix to multiply to a vector or your qubit state. Effectively, it means that you are rotating your z-axis. You're rotating your Bloch sphere along the z-axis 180 degrees. Okay, so now for your assignment, calculate this. Calculate z raised to 2217, x raised to 101, y raised to 50. So you can see these are just matrix multiplication. Okay, so you know this. You will just work to solve this. You work for first with this one, y raised to the 50. Okay, y raised to the 50 is just I. Okay, since this is an even number, so it's just I times this one. So and then you will now be, this will now will be cancelled because this is just I. Okay, x raised to 101 times this expression here. Okay, this is an odd number, so it will be x times this one. So you do the math, and then this one z is also an odd number, so this is also equal to z. So that's going to be your assignment. Okay, the phase gate. The phase gate S is the square root of the Z gate. Okay, so the square root of the Z gate. So this is the representation. S times the ket 0. So since this is the square root of the Z gate, it doesn't change the ket 0, and S times or applied to ket 1 is equal to I times 1. Okay, and this is the matrix representation of the S gate. Effectively, since a Z gate is a rotation along the x-axis 180 degrees, so this is just a square root of Z gate, so it will just rotate along the z-axis 90 degrees or half the Z gate. So meaning, so you can see the rotation is similar in complex number. Okay, in complex number, when you multiply something, it's actually you're rotating or you're adding the phase angle. So if you add the same amount, basically, sorry. So for 90, if you have 290 degrees, so basically you're just multiplying the Z gate here, the S gate here. Okay, so S times S is your Z gate, or the S gate is the square root of the Z gate. Z gate is 180 degrees rotation along the z-axis, but the S gate is just 90 degrees rotation along the z-axis. Okay, we can also get the half of that. We get the T gate. So the T gate, also called the pi over 8 gate, is the square root of S. So this is the representation of the T gate. Okay, if you apply it to 0, it doesn't change because it's a rotation along the z-axis. But it's just a rotation of 45 degrees or pi over 4. Okay, next, important 1-qubit gates. Okay, I saved the best for last. For the 1-qubit gates, I think this is the most important. This is Hadamard gate. Just like what Sir Burns mentioned, in the Hadamard gate, this is where you can apply superposition. So if you want to apply superposition, for example, for those pure gates, the 0 and 1, you want to apply, you apply the Hadamard gate. Because the Hadamard gate turns 0, ket 0 into ket plus, and turns ket 1 into ket minus. So this is your ket 0, this is your ket 1. Your ket plus is here, your ket minus is there. Okay? So this is the representation of the Hadamard H or the Hadamard. H applied to ket 0 is 1 over square root of 2 ket 0 plus ket 1. So this is actually the ket plus. And if you apply it to ket 1, it will result to ket minus. And this is the matrix representation of the Hadamard. So you just multiply this matrix to, for example, your vector here, and it will effectively that it's actually a rotation along the x plus z axis. Okay, so going back, if you apply Hadamard to plus, it will go back to 0. So meaning h squared is equals to I. Now, for your assignment, show that the application of Hadamard to ket minus is equal to ket 1. Okay, just like what is done here. So just somehow the computation here is somehow analogous to the computation here. You will end up with ket 1. Next, also show that the Hadamard applied to ket negative I is equals to I. The Hadamard gate takes a 0 or 1 bit and puts it into exactly equal superposition. So this is the matrix representation of Hadamard. So ket H applied to ket 0 is just this matrix. This is your Hadamard, and this is your ket 0. So this is the resulting vector. And this one is basically the ket plus. Ket H applied to ket 1 is, this is your H, and this is your ket 1. So this is basically your ket minus. Okay, ket minus. We can transition out of superposition without measurement, meaning if you have a superposition, you apply the Hadamard, it will go to either the ket 0 or the ket 1. Okay, we can thus structure quantum computation deterministically instead of probabilistically. So in summary, these are your gates, the important gates. You have the identity, the poly X, poly Y, poly Z, phase S, T, and the Hadamard, and these are the computational basis, action on computational basis, and these are their matrix representation. So basically, quantum gates are just matrix multiplication, matrix vector multiplication. So in general, we can have rotation gates. As you can see, what we did there are just rotate the axis, but you can actually rotate in a specified angle. So you have the rotation gates. You can specify. You can come up with gates with a specified angle. So let me go back to this one. As you can see here, the poly X, poly Y, poly Z, and the T gate are examples of rotation gates because they are rotated. They use rotation on a specific axis, and then you can specify the angle. Now, there are also phase shift gates. Phase shift gates apply rotation about the z-axis. Okay, the S gate and the T gate are example of the phase shift gates. Okay, so basically, gates are just rotation on, when you apply gates, effectively it's just doing a rotation on the Bloch sphere. Sequential quantum gates. You can use linear algebra to compute the effect of sequence of gates. You can actually sequence gates. I mean, apply gates in sequence. Like for example, this one. So H S T H. So the Adamar, and then the S gate, and then the T gate, and then the Adamar applied to the KEDS. So basically, it's just matrix multiplication. So this one is your KED0. This one is your Adamar. This one is your T gate. This one is your S gate. This one is your Adamar again. So you do the linear algebra. By the way, when you draw this in circuits, it will be on the reverse order. Okay. But if you do linear algebra, you actually do you apply first here. For example, in this one, you actually do the operation from right to left. So this one becomes here, okay, and this one, you apply this one to this one, it becomes this one, okay, and then you apply this one to this one, becomes this one, and then lastly, this is your final answer. So I just show you that you can do sequential gate computation. So that's why we can do circuits, because you just apply a series of gates. Okay, next. So that's just the one qubit gate. Okay, but how can we go more than one qubit? So for multiple qubits, we need to first learn how to do tensor products. Okay, so for multiple qubit, you can actually come up with multiple qubit by using tensor product of vectors. So this is your, for example, this is your one qubit represented, and this is your another qubit. So you can actually compute for the tensor product like this one. So this is x multiplied by you concatenate. You multiplied x by the tensor product of this one. So it's basically showing. This is actually a better to understand this example. For example, you have here 1, 2 tensor product with 3, 4. So 1 times 3, 4. So this one, and then 2 times 3, 4 is this one. Okay, you can actually do tensor products of 3 vectors, as you can see here. So this one will now become a 2 qubit state. If you want to have a 3 qubit state, so how many elements here? You have 4 elements. So that's 2 raised to the 2. If you want to get the tensor product of 3, 1 qubit, 3 qubits, so this is the resulting. So you're going to have 8 elements. And this is how you do it here. Okay, so basically this is 2 qubit, and this one is 3 qubit. So in 1 qubit, you represent a state by a column vector, 2 by 1 column vector. In the 2 qubit system, you represent it by 4 by 1 column vector. And by 3 qubit, you have represented by 8 by 1 column vector. And if you have, let's say, 5 qubits, so that's going to have 32 elements. So basically 2 to the n. So these are your 2 qubits. This is the representation. Before we were just using ket0 or ket1. Now we have 4 qubits, 4 2 qubits. We have ket00, ket01, ket10, and ket11. And these are the representation. And it came from, you can do them, it resulted from the tensor products of the original 1 qubit system. Okay, for 3 qubit, you just do it. You just get tensor products of 3 1 qubit state. So this is 0, 0. This is 1 tensor product with 0. You come up with this ket10. Ket11 is 1, 1, tensor product of 1, 1. And ket100, 0, 1, 1, 0, 1, 0. So this is your 1, this is your 0, this is your 0. So if you get the tensor product, it will result to this representation with 8 components. So we call this tensor representation of the product state. is a vector of the size 2 to the n. Note that in this case, you will have more amplitudes. So we should preserve the normality condition that each of the amplitude should be equal to of the norm of the squared norm of the amplitude, or the sum of the squared norm of the amplitude should be equal to 1. So in example, like for example, in this case, this is a valid 2-qubit system, because if you get the squared norm of the amplitude, it will resolve to 1. So meaning this is actually the equal superposition of a 2-qubit system, because there's a 1/4 chance of each collapsing to either ket 00, ket 01, ket 10, and ket 11. Okay, operations on multiple qubits. So I think that the most important gate in 2-qubits is the CNAT gate. Because this will pave the way for this will actually pave the way for interference. Interference and superposition, those are concepts discussed by Sir Burns, by Sir Burns a while ago. Those are very important concepts, and you can actually exhibit interference using the CNAT gate. So the CNAT gate, basically, you have a control bit and a pair and a target bit. So basically, the CNAT gate works like it operates on a pair of bits in which the control bit and the other is the target bit. If the control bit is 1, then the target bit is flipped. If the control bit is 0, then the target bit is unchanged. For example, in this case, the control bit is 0 here, so the target bit is unchanged. But if the control bit here in this case is 1, so the target bit will become will change. So from 10 it will become 11, from 11 will become 10. And the CNAT is represented by this 4x4 matrix. So we're now operating on a 2-qubit system. So we're going to use a 4x4 matrix, not a 2x2 matrix. So this is the CNAT gate. The CNAT gate, or the controlled NAT gate, inverts the right qubit if the left qubit is 1. Otherwise, it doesn't. It's still it preserved what the input. So in this case, CNAT 00 is 00, CNAT 01 is 01, CNAT 10 is 11, CNAT 11 is 10, and this is the matrix representation. So that's the CNAT gate. And you can see here some examples of the computation. So C applied to this 2-qubit 00 will result to 00. C applied to 01 will result to 01 by using this matrix multiplication. But this one, C10 is equals to 11, and Z11 is equals to 10. So that's your operation there. Basically, it's just matrix and vector multiplication. If you're going to use a multiple bit system, we're going to have 2 to the n number of elements. And then we also have this swap gate. The swap gate simply swaps the 2 qubits. And this is the matrix representation of the swap gate. So swap 00, so if you swap them, still the same. Swap 01 will become 10, swap 10, swap 01, swap 11, still the same. So this is the matrix representation. And for a 3-qubit gate, we have these Toffoli gates. So the 3-qubit gate that often appears in quantum computing is the Toffoli gate, or the controlled NAT gate. And this is the this is how the Toffoli works. If you apply it to 000, doesn't change. 001 doesn't change. 010 doesn't change. 011 doesn't change. It will only change here. Here and here, the last two. So that's why you have this matrix representation. Basically, it's just almost similar to the identity matrix, except that in your last 2 rows, the last 2 rows was flipped. Okay, so this is the Toffoli gate. And we can actually implement classical logic gates as quantum gates, as you see here. The NAT gate can be represented by the X gate. The AND gate can be represented by the Toffoli gate. OR gate, anti-Toffoli. XOR can be represented by the CNATs. The NAND gate by Toffoli, and the NOR gate by anti-Toffoli. So this is the table that that shows the different the comparison between the classical logic gates and the quantum gates. Measurement. So I'll just so when we measure a qubit, it collapses to an actual value 0 or 1. So we usually do this at the end of the quantum computation to get the result. So measurement compels the qubit to collapse to 0 or 1. It was not secretly 0 or 1 already. So if a qubit has a value of this one, AB, it collapses to 0 with the probability of the norm of A squared and with 1 with the probability of B squared. So measurement is also an important concept in quantum computing. So key takeaways, the probability is given by the norm square of the amplitude. Qubits can be in superposition and are probabilistic collapse to a classical bit by measurement. Quantum gates are linear maps that keep the total probability to equal to 1. Matrix sets represent operations on qubit. Each quantum gate can be represented by matrix, and the application of a gate to a qubit is a matrix vector multiplication. Operations on quantum computers only use reversible operations. The Adamer gate takes the 0 and 1 bit to equal superposition. Multi-qubit systems are tensor products of single qubit systems, and the number of elements will now be is denoted by 2 to the n. The CNAT gate is a fundamental building block of reversible computing, and complex operations can be built by combining sequences of quantum gates in quantum circuits. And by that, I hope you learned something today. Thank you very much for listening.
Awesome, awesome. Okay, so thank you po, Sir Elmer, and for earlier then, Sir Burns, for the discussion that we had. Sorry everyone for the extension. No, yeah, virtual round of applause. Thank you. Ayan, thank you po, sirs. So yeah, we're very sorry for the extension, pero these concepts are really like the building blocks, are really the fundamentals of quantum computing. So we didn't want to skip out on some of it. So yeah, on your supplementary Google Colab sheets, you would see like an interactive Bloch Sphere. You would also be seeing, yeah, some of the questions actually from the last homework are actually um cube gates already, pero hindi lang namin sinabi sa inyo. So yeah, so we will return your answers to you tonight. So maybe you can look at it at a different perspective, and hopefully now you would be able to answer the questions again. All right. Okay. Okay. So yeah, at this point, at this juncture, we ask everyone to please open their cameras for a photo op. So yeah, hello everyone. Hi, hello, hello.
Okay, I'm waiting for some people to open their cameras before I take the picture. So there's going to be four frames. So I'll take the first one. Okay, ready? 1, 2, smile. Another one for the next frame. Okay, 1, 2, 3, smile. Okay, next one. 1, 2, 3, smile. Okay, last one. 1, 2, 3, smile. Okay, taken it. Chavez.
Awesome. Thank you po. Nice to see you everyone. So ayan, meron pang naka-motor. So keep safe po, Engineer Kent, on your travel. So yeah, thank you for tuning in even though you're on the road. All right, so let me just share my screen. Okay. So the attendance is here. Okay, so again, it will close in an hour, so around 8:30. So please answer that as soon as you can. Konti lang yung questions. Ayan. Okay. All right, sige. Yeah. All right. So after you've answered that, you can leave the call na. So again, thank you very much for tonight. Sorry again for going over time, but yeah, expect sorry. Wait, let me open it. Oh yeah. Okay, ayan, there we go. Please refresh na lang yung yung form. Okay, thank you for that. Ayan. Okay, okay. Sige. All right. So after you've answered that, you can leave the call na. So thank you very much, everyone. Sorry again for the extension. But yeah, expect na ma-return yung mga assignments nyo from the last one so that you can go back at it again and answer it again. All right.
Thank you. Night.
Night,
Thank
everyone.
you, Elmer. Thank you, Burns. Thank you, Javas. Thank you all.